So, dear students, in this class, I am going to discuss question number 5 of exercise 6.2 of simulative triangle chapter 6 of the simulative triangle. Yes or no? Exercise 6.2 question number 5 I am going to discuss about the simulative triangle. Okay. So, in this question it is given that in this question is given that, and you see clearly the DE parallel to OQ. It is given DE parallel to OQ. DE parallel to OQ. Understand? And again given DA parallel to OR. DA parallel to OR. Okay? And we have to prove that EF parallel to QR. Understand? You have to prove EF parallel to EA parallel to QR. You have to prove it. Understand? Okay. So also we can prove it using the concept of the basic proportionality theorem. And as per the basic proportionality theorem, all of you know, if a line intersects the two sides of a triangle, okay, and if a line intersects the two sides of a triangle and parallel to third side, then it intersects other two sides in the same ratio. Once again I am repeating, if a line drawn parallel to one side of a triangle intersect other two sides in the same ratio. Okay. So this is what the basic proportional theorem, all of you know. Let's prove using that theorem. Okay. And here you see in the triangle look at here, in the triangle PQO. In the triangle PQO, and you see the DE parallel to OQ. In triangle PQO, look at here, in triangle PQO, DE parallel to OQ is given. Yes or no? Okay, so you can prove it since DE parallel to OQ. So PE upon EQ is equal to PD upon DO as per the basic proportional theorem. So their corresponding sides are proportional. PE upon EQ is equal to PD upon DO. Okay, this is the by basic proportionality theorem. Understand? Similarly, in the triangle POR, DA parallel to OR. Yes or no? In the triangle POR, what are you finding? DF parallel to OR. Yes or no? You see, DA parallel to OR. So PD upon DO must be equal to DA upon FR as per the basic proportional theorem. Similarly, we can get PD upon DO must be equal to PF upon FR. And this is the point 2 according to what? Thales theorem. Yes or no? Basic proportionality theorem. Okay, same. So from the equation 1 and equation 2 you clearly see PE upon EQ is equal to PD upon DO. From the equation 1 and 2 we are getting PE upon EQ is equal to PD upon DO. Yes or no? From the equation 1. Again in the equation 2 we are getting PD upon DO is equal to PF upon FR. So PD upon DO can be written equal to PF upon FR. So that implies the PE upon EQ EQ is equal to PF upon ER. PF upon FR. PF upon FR. So PE upon EQ is equal to PF upon FR. So since PF, understand, now you got PE upon EQ is equal to PF upon FR. Okay, let's carefully here. Look carefully here. So in the triangle PQR, are you finding anything else? Yes. Are you observing? In triangle PQR, are you getting that? PE upon EQ. PE upon EQ is equal to PF upon FR. Okay. So in triangle, already proved from the equation 1 and 2, PE upon EQ is equal to PF upon FR. Okay. Now see, in the triangle PQR, PQR. Okay. Now EF is a line intersecting PQ at E and PR at F. So, and again we have proved PE upon EQ is equal to PF upon FR. So, according to converse basic proportionality theorem, EF parallel to QR. Yes or no? So, according to converse basic proportionality theorem, EF, yes or no, parallel to QR. Is it clear? By converse basic proportionality theorem. Understand? So this is a very simple problem, and here we can prove, and also here understand how the BPT basic proportionality theorem, Thales theorem and its converse theorem can be useful to verify the properties of any geometrical properties of any geometrical properties of the similarity of triangle. Okay, so this is how you just practice it, and you also observe the different problems, how you are using this important concept, these important properties of the Thales theorem and converse Thales theorem in solving and proving the different kind of geometrical properties. Okay, with this, and see you again for the next class. Thank you.